So we will take the final exam on December 19th during the regular class time. So you know, like the midterm exam, the final exam is the closed book exam. And then the final exam will cover the chapter 4, 5, 4 and 5. And so maybe I believe I can cover some Amdahl's law. So Amdahl's law is in the chapter 6. Okay, so I believe the Amdahl's law can be covered by the final exam. So the final exam will cover the chapter 4, the process architecture, and then the chapter 5, memory hierarchy, and then the actually the early part, the first part of the chapter 6, Amdahl's law. So but actually, there can be uh, questions that ask about the performance. Okay, so which means that you need to also memorize. So you need to also understand how to compare and how to calculate the performance of the computer systems, right? So if you answer the homework questions, then you can find that also the performance question, you can find performance questions, right? Okay, agree. Finally. Okay. So, so I believe we can cover until the introduction to virtual memory today. Okay, and then in the next class, I will complete the chapter 5. So okay, so what did we learn in the previous class? So we learned about the associativity, associativity of caches. Okay, so what does that mean? So we learned that. So in a single cache set, so you can find the cache set here, right? So we can organize the cache has the multiple sets. Okay, and then a single set can include multiple cache blocks, right? And then, to store data in the cache, then we need to store data and tag, right? So, so this slide, so this figure shows that it's a two-way set associative cache, right? So which means that in a single set, we can find two cache blocks, right? We can allocate two cache blocks per set, right? So actually, firstly, when we learned about the cache organization, so we learned about the direct mapped cache, right? Direct mapped cache is so we can say that direct mapped cache is a one-way set associative cache. So which means in a single set, so it's a single set, so we can allocate one cache block, right? So we call, actually for the direct mapped cache, we call this is the index, right? It's a cache index, right? But in a set associative cache, we call this index as the set index. Okay, so for the direct mapped cache, we just call that, oh, this is the index of the cache. So it is because for a single cache set, so we can just allocate the one block. So which means the set index is equivalent to the index of the cache, right? For the direct mapped cache. But for the two-way set associative cache, so actually these figures show that the all caches have eight blocks, but we can allocate the multiple blocks to a single cache set. So this is the set associative cache. So we define a set of a cache, and then we can just define set index of a cache. So which means that we can access the blocks of the cache of this set associative cache using the set index, right? So this is the set associative cache, and then actually using this example, so I showed that. So using the set associative cache, we may increase the hit rate of the cache. So it is because, so I already explained about the disadvantage of the direct mapped cache. So the disadvantage means that actually for the direct mapped cache, actually we can allocate only one block in a cache set. So which means if the multiple blocks, so we may observe that the multiple blocks are mapped to the is a single cache index in a direct mapped cache. So in this case, then we can observe the cache blocks are evicted and allocated again and again. So which means that we cannot utilize the cache efficiently for this case. But so like this example, okay, so it's a direct map, and then two-way set associative cache, and then fully associative cache. So we can observe that using the set associative cache or fully associative cache, we may increase the hit rate of the cache. But I also explained about the cost of this set associative cache or the fully associative cache. So this is because, so when we access a cache, firstly we figure out actually a processor figures out the index of the cache. So for the set associative cache, the processor also figures out the set index of the cache. And then there are multiple cache blocks. So in order to check the request data exists in the cache or not, then we need to compare the tag of the cache block. But in a set associative cache, there are multiple cache blocks per set, right? So which means we need to compare multiple times. But actually, this comparison can be performed in parallel, right? So we can just implement the multiple comparator, right? But it's a cost. So because we require multiple comparators. So, and then fully associative cache, we need to check the tags of entire cache blocks. So which means the fully associative cache requires many comparators. That's why the fully associative cache is the most expensive cache, right? So let's do some example performance. Okay, so this is the hit rate of data cache, so level 1 data cache, and then this the block size is and then we learn the spec 2000 benchmarks, and then blocks there are 60 word block. So we can just measure the cache hit rate using the CPU simulators. Okay, so we can run the benchmarks, and then we can just check the cache hit rate using the CPU simulator, right? So for the one-way set associated, no, it's a direct mapped cache, right? So one-way set associative cache is a direct mapped cache. For the direct mapped cache, the data cache exhibit around the 10% of it's a miss rate. So it's a miss rate, okay? It's a miss rate. And then for the two-way set associated cache, we can observe that the miss rate is reduced, it's a decreased, right? What does that mean? The hit rate is increased, right? So because the hit rate is the 1 minus miss rate, right? So you can observe that the performance of cache is increased. So if we increase the associativity, so it is called the associativity. If we increase the associativity of a cache, then we can observe that the miss rate can be decreased. So then you can think that, oh, then we can use the fully associative cache, right? But if you see the hit rate, so this is this is the hit rate, and then this is the set associativity, then we can observe the hit rate is usually saturated. So it's not linear. It's not linear to the set associativity of the cache. So usually the hit rate of the 8-way or 16-way of the set associative cache is similar to the hit rate of fully associative cache in a CPU. Okay, so what does that mean? The fully associative cache is the most expensive cache, right? The cost is high. But if we just compare the hit rate of the 8-way or 16-way set associative cache with the fully associative cache, then we can observe that the hit rate is actually similar. Then we don't need to use fully associative cache, right? Because the hit rate is usually saturated. Okay, so that's why we do not use fully associative cache in a CPU. So if you read the CPU specification, then you can find that actually the Intel CPU or AMD CPU usually use the 8-way or 16-way set associative cache, right? So this is the set associative cache, and then this is the example organization of set associative cache. So what is the associativity of this cache? So how can we figure out the associativity of this cache? We can just count the comparator, right? There are 4 comparators. So which means when we access the target cache set, we need to compare the tags of 4 cache blocks. What does that mean? So this is the 4-way set associative cache, right? Right, because in a single cache set, so this is the set, this is the set. In a single cache set, we can observe there are 4 cache blocks. So this is 4-way set associative cache. So in address field, so this is the 4-way, it's a 4-way set associative cache, right? Set associative cache. And then, so this is the address field. And then what is this? This is the block offset, right? And then, the block offset occupies 2 bits of the address field. So what does that mean? the block size, the one block size of this cache is 4 byte, right? Because block offset is 2 bit. And then, so this is the index of the cache, but this index is the set index, right? Because this is the set associative cache, the four-way set associative cache. So what does it mean? The set index is 8-bit. So which means this cache includes 2 to the power of 8 sets, right? So this is the 256. 256 sets. There are 256 sets, but each set include 4 cache blocks. Then what is the total number of cache blocks? It's multiplied by 4 because this is 4A. There are 1024 cache blocks in this cache. And then I mentioned that I mentioned that the size of a single cache block is 4 byte. So what is the size of this cache? The size of this cache is 4096 byte. This is the 4 kilobyte. Okay, we can calculate the cache size like this. And then, the address field is the 32-bit. And then the remaining bits are tag bits. Okay, so which means that we can observe the 22-bit is used as the tag of this cache. Okay, so when a set index is figured out from an address, then we can access the target set. Then we can read the tags of 4 cache blocks. Then these tags are compared with the tag field of the address, right? So you can find that this tag field is compared with the tags in the target set, right? And then if the cache block includes the valid block, so we need to check the valid bit, right? And then if one of the tags is matched, then it's cache hit, right? So you can find the hit here. And then if the cache is hit, then we can read the request data from the cache, right? But it's multiplexed. So that's how the set associative cache works, right? Okay, so and then for the set associative cache, then we need to also consider replacement policy. So what is the replacement policy? So if the target set is full, so what does that mean? So the load word instruction is executed, then this is the missed in the cache. So what does that mean? We need to allocate new cache block, right? Because the load word is executed, this is the missed, so which means that we cannot find the requested data in the cache. Then this data block is fetched from the low-level cache or memory, and then the fetched block is newly allocated in the cache. But let us assume that the target set is already full, which means all cache blocks are valid, right? So in this case, one of cache blocks needs to be evicted, so kicked out from the cache, right? But we need to select. We need to select from these 2 blocks. How? So when we actually for the direct debit to cash, we don't need to consider about this replacement policy. So this is called the replacement policy of the cash. So which means that we need to select the cash blocks which will be evicted when a new cash block is allocated. So this is the replacement policy. For the direct debit to cash, each set include only one cash block. So we don't need to consider about the replacement policy. So which means if a new cash block is allocated, then the old cash block is just evicted. But there are only one existing cash block. But for the set associative cache or fully associative cache, we need to select which block will be evicted, right? Because there are multiple valid blocks, right? So then how can we select the evicted block, the blocks which will be evicted? How? So think like this. So this is the block A, and then this is the block B. Then if we know, among between these two blocks, so we can know, block B will be used in the future. Then we need to evict the block A, right? Obviously. So if we know, block B will be used in the future, then among two blocks, so we can evict the block A, right? What's the problem? This is a future event, right? We don't know. We don't know about the future, right? We can just predict, but actually this is related to the access pattern of our program, but actually it's not easy to predict the access pattern. Okay, it's just a prediction because this is a future event. So we know. So if in the near future, if this B is used, then we can evict this A, but it's not possible, right? Because we don't know. We don't know about the future. So actually, we can implement some various cache replacement policies, and then this is the mostly used. Mostly used cache replacement policy. This is called the least recently used LRU. So what does that mean? Least recently used. So you know this is the least, right? The least recently. So which means that among A and B, if B is recently used, then A is the least recently used, right? So it's a least, right? So in this case, we evict the block A, right? So this is the LRU policy. So which means if a certain block is least recently used, right? So it's used very the long cycles ago, then we just evict this block. So it's the LRU policy. The LRU policy is frequently used in the CPU, and then it is reasonable actually because the cache exploits the data locality, right? And then we learned about temporal locality. And then based on the temporal locality, if a certain block is least recently used, then we can expect that, oh, this block will not be used in the near future, right? So that's why we frequently use least recently used LRU policy for the cache replacement policy. But problem is that, so it's not easy to implement the LRU policy, right? So true LRU policy. So usually the Intel or AMD implements the pseudo LRU, not true LRU, okay? So because it's LRU policy is simple for two-way, but so if the if we use the if we increase the set associated with the cache, then it is difficult. It is difficult to implement the LRU policy. So that's why the CPUs implement the pseudo LRU. It's similar to LRU, right? Sometimes we can implement the random policy. So which means that the blocks which will be evicted can be selected randomly. Okay. So usually ARM CPUs implement the random replacement policy. Okay. And then, so so we learned that the cache can be also organized hierarchically. So which means that we can organize the L1, L2, and L3 caches. And then if you read the CPU specification sheet, then you can find that the commodity CPUs include until L3 caches, right? So, and then let's see the benefit of a multi-level cache. So this is the some assumption. The baseline CPI is 1, and then clock rate is 4 gigahertz, and then the bit rate per instruction is 2%. And then let us assume that the main memory access time is 100 nanosecond. Then how can we calculate the CPI, the CPI by this memory system? So we can calculate the miss penalty, okay? Because the clock rate is 4 gigahertz. This is the clock period of CPU. And then the main memory access time is 100 nanosecond. So the miss penalty. So if the cache miss is observed, then the miss penalty is 400 cycles for this CPU. Then what is the effective CPI? So this is a miss rate per instruction. So the 1 plus is baseline CPI plus 0.02 multiplied by 400, it's 9. So what does that mean? CPU is very fast, and then, the main memory is slow. And then if we just use the only level 1 cache, the effective CPI is 9 times of the ideal, the baseline CPI, which means if we just consider the latency of the main memory, then performance is 9 times lower than the ideal CPU. It's a huge performance drop, right? But if we just add the L2 cache, and then let us assume that the access time is 5 nanosecond, because the cache is in the CPU chip. So this is the on-chip cache. So, if you open actually it's not easy recently, but if you see some main board, the main board of the CPU, the computer system, then you can find that this is the main memory, and then this is CPU, because we just use DRAM as the main memory. And then caches are inside of the CPU chip. So which means caches are much faster than the main memory. So this is the off chip. So the main memory is the outside of the CPU, and then the caches are inside of the CPU chip. So cache is much faster. Also, we use the SRAM for the cache memory cells, right? So SRAMs are also the faster than the DRAM, right? And then this is the global miss rate to main memory. It's a 0.5%. Okay, so you can find that the miss rate can be also reduced, right? So it's a L1, L2, right? And then usually the size of L2 is larger than the size of L1 cache. So which means we can also reduce the miss rate. The miss rate for the L2 cache, right? So this is the primary miss with the L2 hit. So which means that this is miss in the L1 and then but it's hit in the L2. So okay, this is the 20 cycles. And then if the L2 miss, so if the request is missed in the L2 also, then we can just consider this is the L2 miss penalty, right? So 400 cycles. So in order to access the main memory, it takes 400 cycles. So this is the CPI. So you can observe that the CPI is reduced, right? And then what is the performance performance comparison based to the level 1, the L1 cache system. So we can observe that the performance is increased by 2.6 times, right? So what is the benefit? What is the benefit of the multi-level cache? So benefit is that we can I mentioned that the caches are much faster than the main memory, right? And then but if we can also use the larger cache. So the L2 caches are larger than the L1 caches. So which means that we can reduce the miss rate to the L2 cache. So to main memory, request to main memory, then we can reduce the miss penalty of the level 1 miss, right? Then we can increase the performance. Okay, so usually level 1 cache size is very small. So it is because you need to minimize the hit time, the access time of the L1 cache. So which means we need to make very fast caches for the L1 cache. But if the cache size is small, then we can observe that the miss rate is usually high, right? So we can use the L2 cache. L2 cache size is larger because we want to reduce the miss rate using the L2 cache. But so size is larger, but it's slow. But using the L2 cache, we can observe that the performance can be increased, right? So this is the benefit of the multi-level cache hierarchy. Okay, so like L1, L2, L3. Okay. Okay, so this is the multi-level cache, And then actually we do not learn about the out of order CPU, but usually what the commodity CPUs are, the most commodity CPUs are out of order CPUs, not pipe, not in-order CPUs. Actually, we learned about the in-order CPU in chapter 4, right? But you know, the Intel CPU, AMD CPUs, and then also ARM CPUs implement the out of order CPUs. So usually, so it's not easy. For the out of order CPUs, it's not easy to analyze the impact of cache because the instructions are executed out of order. Okay, but you can learn about the out of order process architecture in the advanced computer architecture course. So actually at Korean University, the advanced computer architecture course are provided for graduate student. Okay, but okay, so then let's see the interaction, the cache in cache performance by software implementation. Okay, so let's see the some example of the matrix multiplication. Okay, so matrix multiplication is very simple, right? So very simple application like the C equal A multiplied by B. Then when we implement this matrix multiplication, if we consider the impact of cache hierarchy, then we may optimize this matrix multiplication program. So what does that mean? Actually, the programmers do not consider about the cache usually. So it is because, as I mentioned, the caches are managed by hardware, not software, right? So actually, which means the cache, we cannot use any instructions to manage cache data, but we can write code by considering the impact of caches. Okay, so let's see the example. C equal A multiplied by B. This is the matrix multiplication kernel, right? And then, you know, we can implement the matrix multiplication like this, right? It's a very simple code, right? Then what is the performance issue? What are the performance issues of matrix multiplication? So actually, in order to calculate this element, which data is required. So we require the entire row elements of the matrix A, and then the column of matrix B, right? Then for this element, we require this row and then this column. This element, we require this row and then this column. What can you observe? For the matrix multiplication kernel, okay, so the code, row data of matrix A are repeatedly used. So what does that mean? We can observe high data locality, strong data locality, right? These elements, these data are repeatedly used. But how about the column? Column data is used here, 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 right? Like this. So actually, for the single row computation, for this single law computation, we cannot observe locality for this matrix B. But we can also observe the locality of matrix B. Why? In order to calculate the next law of the matrix C, then we use this law for the matrix A, then columns of this matrix B are also used. So what does that mean? We can observe the locality. So which data will be used, and then after long cycles, because we need to calculate these elements first, then after long cycles, then the same column will be requested again. So which means we can observe the locality, right? So, and then in order to calculate the entire element, so we already know that these columns will be requested again and again. But what's the problem? The gap. This gap is larger than the access pattern, the locality of these low elements. So which means in order to calculate this law, so we can observe that the raw data is requested again, 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 again. Okay, so this gap is very, very short, right? But for the column data, this gap is large. Then what's the problem? The problem is that, actually we can observe the locality, data locality in the matrix multiplication. But if the cache size is small, so this is the problem, right? Then this column data firstly allocated in a cache, but when the same column data is requested again, then because of the capacity of the cache, limited capacity of the cache, the old column data can be evicted from the cache, right? Because before the same column is requested, then we can know that other data, the other columns of this element, this amount of columns needs to be requested first. So which means if the cache size is small, then this column data is evicted from the cache. That's the problem. So what's the problem? If the matrix size is large, so larger than the cache, then even though we can observe the data locality between this column data, but this data locality cannot be utilized in the cache. Okay, this is the performance issues of the cache. Okay, so as I mentioned, the programmers cannot manage cache data, but the performance of programs can be highly influenced by cache structure, the cache hierarchy. Then how can we tackle this issue? What's the problem? We can observe data locality, but this data locality is not utilized well. It is because cache is small, and then matrix size is large. How can you solve this problem? We cannot adjust the cache because the cache is hardware. We can adjust the size of a problem. Blocked matrix multiplication. So blocked matrix multiplication. So this is the algorithm part, right? So That's why we need to learn about the algorithm, right? So actually, when we perform C equal A multiplied B, so we can, so using this so very simple program, that we can also calculate the C equal A multiplied by B. But in order to reduce the size of the problem, then we can split the matrix into the multiple smaller submatrices, like here and here, here. Then we can perform the matrix multiplications using smaller submatrices. So by doing this, we can reduce the size of matrix. So it is because the performance drop. The performance drop of this matrix multiplication is caused by large matrix, right? Large matrix. So if we reduce the size, then we can tackle this problem, right? So by applying the blocked matrix multiplication algorithm, we can increase the performance. So this is the optimized program that by considering the cache hierarchy. Okay, so, and then this is a very important, very important technique, right? Because why do we learn about the computer engineering or computer science? Because we want to develop the fast and efficient computer system, the high performance, which uh, high performance computer system, right? So which means we need to also optimize our program by considering the hardware architecture, right? So this is the example. It's a very popular example of the optimization, the kernel optimizations, considering the hardware architecture. Okay, let's see the performance. So you know, so in this graph, so you can find the y-axis is the gigaflops. So it represents the throughput of the floating operation, right? It represents the throughput, which means performance, right? And then you can also find the size of matrix multiplication. And then, so this is the unoptimized, then this is the blocked. So which means that the blocked matrix multiplication. So for the unoptimized version, the matrix size is increased. So you can find that the performance is dramatically reduced, right? So 0.8 and 1.7. The performance is nearly the half of this small matrix. But if we just apply the blocked matrix multiplication, we can find that the performance drop is very small, right? So what does that mean? So in order to make the efficient computation kernel, efficient program, then we need to consider the hardware architecture, right? And then actually this is more critical recently, right? Because we are using very large scaled workload like the AI workload. AI, the recent LLM models, the large language models, LLMs actually handle the huge amount of data, right? Which means the applications need to be optimized for the target system. Okay, that's why we need to understand. We need to understand the target computer systems, target computer hardware. Okay, this is some optimization. And then this is also summary of the cache. So you can also read the summary of caches. Okay. Okay. Here and replacement policy. And then we also learned about the right policy. And then, so I can just explain about the source of misses. So when we analyze the performance of cache, then we can also analyze why cache misses happen. Why cache misses happen in this cache, a target cache. So this is called the source of cache misses, and then this is also called the 3Cs of cache. So it is because the sources of cache misses start with the C. So there are three types of cache misses. It's the compulsory misses, like also this is called the cold miss, and then capacity miss, and then conflict misses. So actually, these three C's of cache explains why cache misses. Why cache misses are why cache misses are caused in the target cache. Sorry. So compulsory misses or cold misses represent the cache misses when the data is firstly requested. Do you understand? So I mentioned that initially the caches are empty. And then also obviously when a certain data, like load word A, certain data is firstly requested, we cannot find this data in the cache, right? In order to find the request data in the cache, then the data needs to be requested earlier, right? Then the data will be allocated in a cache, and then we can just access this data. So actually, and then firstly, if the data is firstly requested, then this is miss, right? And then this type of miss is called the compulsory misses or cold misses. So cold. It also start with the C, so cold miss. So this is the cache misses when the data is firstly requested. And then capacity misses. The capacity misses represent the cache misses by capacity limit. So, the cache size is small, okay? And then because of this cache, then we can also observe cache misses, right? So, and then, so this is called the capacity misses. And then conflict misses. The conflict misses represent the cache misses caused by associativity of cache. We already know that the fully associative cache exhibit the higher hit rate, right? But if we use the set associative cache or direct mapped cache, then we can observe the cache hit rate. So cache miss rate is increased. The hit rate is reduced, which means the miss rate is increased. So what does that mean? Because we use set associative cache or direct mapped cache, then misses are also increased. So these misses are called conflict misses. So these sources of misses, these sources of misses are called the 3 Cs of cache. So it represents why cache misses are caused. Then, so and also we can also consider some cache configuration, and the effect on the cache misses. So we can also increase the cache size, then capacity miss will be reduced, right? Because if we just increase the cache size, then capacity miss will be decreased. But what is the negative performance impact? Access time, which means heat time can be increased. So I also explained that the Aeron cache size is small because we want reduce the heat time. We want to decrease the heat time. But problem is that if we just use the smaller cache, then capacity miss will be increased. Associativity, then we can also decrease the conflict misses, but access time can be increased. Also, the cost is also increased. Block size. If we increase the block size, we can reduce the cold misses, compulsory misses. Why? So I mentioned that, if the data is firstly requested, then this request always causes cold misses, right? But this table explains that if we increase the block size, we can reduce the cold misses or compulsory misses. Why? Think about the load A0, load word A1, load word A2, right? For the array data, if we just increase the block size, then this block will include the A0, A1, A2, blah, 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 blah. So actually, this load, the first load, this load will cause cold miss, but actually we can observe heat, right? So if we increase the block size, then we can reduce the cold misses. But what's the problem? Negative impact. Negative performance impact is the miss penalty is increased, and then the cache can be polluted, right? So actually, uh, this design, so we can also observe the design trade-off for the cache configuration. Okay. Okay, so this is the end of the cache. Okay. So, and then I will explain about some another important topic in the memory system, the virtual memory. So until now, so I just explained that it says load word in A, then we firstly access the cache, and then if the cache miss is encountered, then the main memory is accessed. And then we just define that load word A, which means load word just fetch data in main memory in the register file, right? That's what we learned until now. But actually this address requested by load instruction, also the store instruction, is the actually virtual address. What does that mean? Why? So you can find virtual. What is the meaning of virtual? It's fake. It's not real. So what does that mean? So actually, the the virtual memory means that uh, the original purpose of the virtual memory is to use the original purpose is to use main memory as cache. So which means, so actually, so in an old computer system, DRAM, DRAM was very expensive, and then also the DRAM size was very, very small. So actually for the Intel 86 or 88 computers, then the size of main memory is around the 640 kilobyte. So kilobyte, 600 kilobyte, around the six, it's smaller than the 1 megabyte, right? Very, very small. It's because the memory is small, but memory was also very, very expensive. So, but the hard disk drive is a storage device. Hard disk drive is it's a cheaper than it was cheaper. It's still cheaper, right? So the hard disk drive is cheaper than the main memory, and then also it has large space, right? So actually, the virtual memory is designed for using this main memory like a cache. So what does that mean? Actually, we can store the data in the hard disk drive, and then the frequently used data can be stored in the main memory, right? So virtual memory concept is developed for this purpose, right? So it means using the virtual address, actually, even though the physical memory, so it's a real memory, even though the physical memory size is very, very small, we can just define virtual memory space to the hard disk drive. So, this is very large, right? So we can access the hard disk drive. But what's the problem? Hard disk drive is extremely slow, right? So in order to access this small DRAM, then we just translate this virtual address into the real memory address. It's called the physical address. It's a physical address. Then we can access this real main memory. So this is the concept of virtual memory. So to the programmers, the computer system just provides the virtual memory space. So virtual memory space is very large. It's larger than the physical memory space. The physical memory is the real memory, right? So actually in the computer system, virtual represent the fake, okay? And then physical represent the real, okay? So real memory size is very small. So in order to access the data in this real memory, the virtual address needs to be translated into the physical address, right? So it's like this. Uh, our computer system has a very small physical memory. It's a real memory, right? But programmers do not like this situation, right? And then we already learned about the data locality, right? So which means we can use the physical memory as cache. So instead of provide this small physical memory space, computer systems provides the large virtual memory space to the programmer. So which means that, programmer think that, to do this computer system, that we can use the very large memory space. So we can make the, we can execute the load instruction using this virtual address. But in order to access the data in the physical memory, then virtual address needs to be translated into the real address, the physical address. Okay, so this is the virtual memory concept in a computer system, right? Then you can think that, recently the main memory size is very large, right? Then also the server system, but actually the high performance servers includes the terabytes of main memory, right? Then you can think that, we don't need to use virtual address, virtual memory space, right? Because the the physical memory is currently very large. But we still use virtual memory. So it is because using the virtual memory, we can easily manage the memory space. So actually the virtual memory is managed by operating system. But the hardware also needs to support this virtual memory space, the virtual memory. So it's called the memory management. So you may heard about the MMU, so memory management unit. So this is the hardware components that supports the virtual memory. Then why do we need to use the virtual memory concept currently? So it is because the physical, the, the physical memory space or physical memory configuration is various. But if so, which means that for the different computer system, it keeps the different physical memory. So if an application directly access the physical memory, then programmers need to consider these various situations. It's very complex, right? Right? So actually operating systems manage this virtual memory. So virtual memory to physical memory conversion, right? So the programmers just think that, we can access the very large memory, the virtual memory space only, right? But some management are performed by operating system and hardware. And then another reason is that actually in a single computer system, we run multiple processes. So what's the problem? For example, so I am using Chrome, okay, right? The Chrome. Then I also launched the Chrome multiple times. What does that mean? I just execute the same binary code multiple times. So like the Chrome A, Chrome B, Chrome C, right? So because the binaries are the same, so which means that Chrome binaries includes the same load, same load, same load, same load instructions, right? So A is accessing some data, B is accessing some data, C is accessing some data. What's the problem? Because I launched the Chrome browser multiple times. So actually, these processes need to access the different memory location, obviously, right? Because these are different processes. Hopefully, even though the binaries are the same, the processes are different, right? And then because the processes are different, these processes need to access the different memory location. But it's not possible, right? Because big binary is the same. So so this address is actually fixed. So CA also execute the load AA, CB also execute the load word A. What's the problem? Even though the data is separated, then we cannot manage this situation. So operating system provides the different virtual memory space. Okay. So actually different converting rules. So I mentioned that the virtual address needs to be translated into the physical address. So if we just use the different converting rules, then using the same virtual address, we can access the different data location. Right? I mentioned that the physical address is the real address, right? So why do we use the virtual memory space? In order to manage multiple concurrent processes. Okay, so memory management needs to be supported by operating system, and then operating system needs to handle multiple running processes, right? So, and then in order to distinguish some different location, the different location in the physical memory, then operating system just applies some different translation or converting rules for the virtual address to the physical address. Do you understand? So you may think that, oh, so until now, I explained like the load word just directly access the physical main memory, but actually this load word just access the virtual memory space, and operating system just convert the virtual memory address to the real physical memory space. So this is the virtual memory concept. Okay. And then I explain about the original purpose of virtual memory. So original purpose is to use main memory, the fast main memory like a cache, right? But actually in the modern computer system, we use virtual memory concept to manage many concurrent processes. Okay, so also the virtual memory is also controls some the permission of data, some security issues in our data. Okay, so and the operating system manages this virtual memory, the virtual memory. Okay, so just this, and then in the next class I will explain how this translation, the virtual memory to physical memory space translation is performed. Okay. Thank you for your attention. See you in the next class.